Alright everyone, this is the last video for Monday and Tuesday this week. And we're going to be talking about continuous compounding. On the last one we talked about compounding where you could have compounding periods of monthly where it's happening 12 times a year, semi-annually where it's 2, or quarterly where it's 4. This, with continuous compounding, it's a situation where the compounding periods increase infinitely. And it says infinitely, but usually they're usually based on how often they can do the calculation. So for instance, the period could be every trillionth or even a quadrillionth of a second. So we're talking about millions, billions, trillions, quadrillions of times per year. Even way more than that. So when you think about that previous example where our n was 12, that's a pretty big difference. So we have a new formula for this one to account for that change, and that's A equals P e to the RT power. Now keep in mind that e is not a variable, it actually has a value. It's basically the opposite of a log. So if there is a special button in our calculators for this. It's right here, it says e to the x. Note that it's on the natural log button. That's what the ln stands for, is natural log. It's the opposite of natural log. So if we hit second on here to get to the second function there, and we hit that button, it's going to give us something that's e to the some power that's going to be inside those parentheses, which in this case will end up being our RT. So when we're looking at that e, it's not just a simple variable of e. Now our A, P, and our R and T are exactly the same. You might note that N is actually missing from this, and that's because it's increasing infinitely. The periods are increasing infinitely, so we can't actually list that as a variable there, which is where the E comes into play. It takes the place of that. So for example, let me jump in here. These are actually, I want to say, fairly easier to calculate because a lot of it is just calculator work. I mean, we've had mostly calculator work here, but we can kind of put this all together in one giant thing plugged into the calculator. So our formula is that A equals P to the E RT. Although I probably should color that out for you, so we'll say our future value is purple of that A. Our principal is going to still be red. Now I'm going to go ahead and write the E in black because that's always there. It's always E. And then it's to the power of R, our rate, times time, which is our T. So our example here, it says you decide to invest $8,000, our principal, for 6 years. So we're given our time right off the bat at 6 years. And you have a choice between two accounts. The first pays, there should be an S there, first pays 7% per year, and it's compounded monthly. So this is something that's a key here. This one's compounded monthly. The second pays 6.85% per year and is compounded continuously. So this is the important piece. And we want to know which is the better investment. So we actually have two options that we're choosing from here, and we need to tell them which is the best. One of these is going to use our A equals PERT, which is at 6.85% per year that's compounded continuously. And then the first one that we need to deal with is 7% per year compounded monthly. Now note the rate is a decent amount higher on the first one, the 7% versus the 6.85%. The difference then comes in where it's compounded monthly versus compounded continuously. So the first equation we're going to use is actually that same equation we just used above, where I'm going to say this is investment 1. And this one over here will be investment 2. Investment 1 and investment 2. Now investment 1 is going to use the formula that we just used before, where we have the A equals P times 1 plus our rate over our number of compounding periods, N, and that's going to be raised to the power of n times our time in years. So let's go ahead and do investment 1 first. I'm going to kind of blow through it because we did one up above like this. So go ahead and plug in our principal, which is $8,000. That's going to be multiplied by 1 plus, and then in a fraction, our rate, which is 7%, so I'm going to write it as 0.07, over our compounded period. It's compounded monthly, so we're again using 12. Note that it's not always going to be 12 like the two examples we've had here. And that's to the n, our compounding period, times our time, which our time changes in this one to being 6 years. Now, I'm going to kind of do what I did before with the calculator. Bring the calculator out here. I'm going to go ahead and do that 12 times 6. So that's going to give me 72 is what's going to be outside, up above there. So I'll write that down. This is going to end up being 72. I'm going to bring down this 8,000. And then inside the parentheses, I'm going to do that calculation here, which is that 0.07 divided by 12. That's going to be 0.05833333, and I'm going to go ahead and just add that to 1. And that's going to end up giving me 1.005833333. Now, the problem with that is that that is a very big decimal. So what I'm actually going to do is I'm going to cut it up a little bit. I'm going to cut off a piece of it. So I'm going to make this 1.00, and then it's 5833 repeating. I'm just going to put 583. Now, that's still a pretty long decimal to write down, but it does work that way. So if we take that 1.500583, and we're going to multiply that by, oh, actually we need to do the exponent first. We're going to do that 1.00583 to the power of 72. So again, I'm using that caret button. That caret button I was using, sorry, it's not on the screen, caret button I was using before. Raise that to the power of 72, gives me a big long decimal there, and I'm going to multiply that by my principal of 8,000. That's going to give me 12,157.9427. So I'm going to go and cut off the end of that there and just make it that final value there. So our A for this one equals 12,157.94. That would be my future value on investment 1. So now I need to work with investment 2. And investment 2 will be a little bit quicker because it's heavily calculator work. So our formula for that, it's A equals our principal times E to the power of RT, our rate times our time. This is sometimes called PERT. If you ever hear me say that, that's what I'm referring to. So we plug in the values, same values we used for those on the previous one. It's 8,000 times E to the rate, which the rate actually is different on this. It's 6.85%. So I'm going to go ahead and write that as 0.0685. I have to convert it to decimal. And then that's going to be multiplied by the time, which is still 6 years. So same time, same principle. The rate does change. And for this, there is no compounding period because it's instead replaced by the E. Now, these are basically going to be mostly calculated work. So we're going to plug it in kind of exactly like it is. So I'm going to take that principal of 8,000. I'm going to hit second and that LN button because that's where E to the X is. And it's going to give me an E with a caret and then parentheses, and that's what this is going to go inside of. So it's going to be 0.0685, and then that's going to be multiplied by 6 up there. And you want to make sure when you do the end of it, go ahead and close that parenthesis, because if you don't close that parenthesis, sometimes it will give you a weird answer. So if we go and hit enter on that, that's going to give us that our future value for continuous compounding will end up being $12,066.60. So if you note here, if you look at the difference between these two, you actually find out that if it's continuously compounding for 6 years, it actually comes out to be slightly less than if it compounds only 12 times per year at 12,157. So the better investment would be at 7% compounded monthly. So the big piece there being that the rate makes the big difference at 7%. So you would, in this case, choose investment 1. This is better. All right, if you have any questions, please get with me during the hour Monday or Tuesday.